So now we're going to talk about sequences. And what exactly do we mean by a sequence? Well, here are some examples. This is a sequence. It's number 1, followed by 2, followed by 3, followed by 4, and so on. Okay? So there's actually an infinite number of numbers here, right? And the whole thing is what we call a sequence. Here's another one. 1, 2, 1, 3, 2, 1, 4, 3, 2, 1, and so on, right? That's a sequence, and I think you can see a pattern, you can see a rule for discovering all of it, right? It doesn't have to be obvious, right? You know, it could just be kind of a mysterious sequence, just a bunch of numbers. Like, for example, a sequence of the temperature values of Laramie, you know, is just, you know, kind of oscillates between, you know, minus 40 and 90 or something like that. Here's another kind of sequence that we could have. It could be 1, 4, 9, 16, and so on, right? Again, you can see a rule, you can see a pattern. That's not really the important part, right? But a sequence is just this. It's just the number and then another one and then another one and then another one, right? That's informally what a sequence is. Now, let's take a look a little bit more formally or mathematically what we mean by a sequence. And the way we're going to define it is that it's a function from the natural numbers to the reals, okay? Or some other set. It's not, you know, it's the same definition. So, for example, let's say that I think of 1, 2, 3, 4, and so on, right? Well, that's f of 0, f of 1, f of 2, f of 3, and so on, right? And here f of x is equal to x plus 1, right? That's the function that we're using, right? F of x, let's say g of x, right? Some other function could be x plus 1 squared, and then we get 1, 4, 9, and so on. Okay, so yeah, we can actually think of a sequence as a function. And if you're thinking to yourself, that's kind of unnecessary acrobatics, isn't it? I mean, sequence was fairly well understood before we did this function stuff. Yeah, I sympathize. Okay, I agree with you. But think of what we're doing. We're actually trying to make life easy on ourselves, because we've already learned stuff about functions. Functions are things that we understand and we can manipulate and we have theorems about. So when we're trying to learn about sequences, we can reuse all of that knowledge, right? That's kind of the point. So we can reason formally about sequences because that's just reasoning formally about functions. Awesome. Okay. Now, notation-wise, we like to write a sub I instead of a parentheses I, right? Yeah, we might think of it formally as a function, but we still like the idea that it's just a1, a2, a3, a4, and so on. And this is what we do when we want to refer to the whole function, okay? We just put a sub n in curly braces, okay? And I'm not entirely sure why somebody thinks that that's a sequence and not the set containing a sub n, but that's kind of universal notation for sequence, okay? Here are some examples, and these are, you know, we've done some of these before, like 1, 2, 3, 4, 5, 2, 4, 6, 8, 10, 1, 1/2, 1/4, 1/8. You can actually see the pattern there. You know, it's like 1 over 2 to the end, something close to that. We have here 1 minus a half, a third minus a fourth. Again, that's just a standard sequence, right? The formula for that is something reasonably close to 1 over n, could be 1 over n plus 1, and minus 1 to the n, or to the n plus 1, depending on where we start. Okay. So anyway, so here are kind of the rules that we use for that. And here, I'm actually always starting at 1, not at 0. So like I said, it just depends, right? I say it's from the natural numbers, but it really doesn't matter. It just needs to be from some ordered set like that. What is important is that there's a first one, a second one, a third one, etc. Okay, so now let's look at a very special kind of arithmetic sequence, and rather a special kind of sequence, and that is an arithmetic sequence. So here's an example of 1, 1, 2, 3, 4, and so on. Okay, and what makes it an arithmetic sequence is when I look at the difference between these two is 1, and the difference between those, 3 minus 2 is 1, and the difference between those, 4 minus 3 is 1, and so on. So I can always get the next number by just adding 1. Okay, so what I have in this case is a is equal to 1. That's actually pretty easy because it's just the first element in the sequence. Okay, and d is equal to 1. That's the common difference. So I start with a, that's the first element, and then I add d. Okay, and then I add d again, since I already have a plus d is a plus 2d, and then a plus 3d, and so on, right? And then kind of the nth element or something like that is a plus nd. Okay, now this is 1, this is 2, this is 3. This is actually the n plus 1 element. Okay, and again, that's just being careful about where we count. A and d can be reals. Of course, the n is an integer because it's the nth term in the sequence. Okay. Okay, now this is a way of actually defining an arithmetic sequence. A sub 1 is equal to a sub n is always a sub n minus 1, the previous element, plus d. And here's another way that I can define it. I can just say is given by a sub n is equal to a plus n minus 1d. So this is what's known as a closed form solution. And the reason it's called that is because you notice that this part does not depend on any previous term. Here we have what's known as a recurrence relation. And to be honest, that's just a recursive definition, right? That's really what it is. So we have here a recursive definition, and we have here a non-recursive definition. Okay. An arithmetic sequence can be defined either way, and of course, I'm sure you can see this coming. You can actually prove that those two definitions are equal. Okay. All right. So again, here are some examples of arithmetic sequences, and what I have here is a is equal to 1. A is easy. It's just the first element, right? In here, a is equal to 3. In here, a is equal to 3. Now, d is the common difference. So 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1. Yep, common difference is 1. Here, the common difference is 7 minus 3 is 4, 11 minus 7 is 4, 15 minus 11. Yep, d is 4. In here, we have minus 2 minus 3. Oh, that's minus 5. Minus 7 minus 2, yeah, that's minus 5. Minus 12 minus 1, yeah, okay. So d is actually minus 5. Okay, so this is how you can get the values of a and d if you see an arithmetic sequence. And if you don't get the same value of d for repeated differences, then it's not an arithmetic sequence, right? So 1, 2, 4, d starts at 1. For the next step is 2. Nope, not arithmetic. Okay, all right. The other kind of important sequence is called a geometric sequence. And instead of the common differences, right, that are the same, this one has common ratios that are the same. So for example, everybody's, by which I mean everybody who's a computer scientist, favorite geometric sequence is 1, 2, 4, 8, 16, 32, and so on. Okay, so 2 divided by 1 is 2, 4 divided by 2 is 2, 8 divided by 4 is 2, 16 divided by 8 is 2, 32 divided by 16 is 2, 8 divided by 4 is actually 2, not 4. What was I thinking? Okay, and so what we have is that we have a common factor, right, of a sub n plus 1 divided by a sub n, right? That's always the same. Okay, so what it looks like is a, which is the first element, in this case 1, and here our common factor r is equal to 2. So I say 1, and then 2 times 1 is 2, 2 times that is 4, 2 times that is 8, and so on, right? So that's how I can recreate this sequence. And again, here's how I can give the recurrence relation, right? Or the recursive definition. So a1 is equal to a sub n minus 1 times r. Okay, and we also have kind of the closed form or the non-recursive definition where a sub n is equal to a times r to the n minus 1. By the way, it's always tricky whether it's to the n or to the n minus 1. Is it n minus 1 times d or is it n times d? Don't stress about that. What you want to do is just figure out what happens when n is equal to 1 and make sure works, right? So when n is equal to 1, a to the r to the 0, well, that's just a. Perfect. That's what I need it to be, okay? So that's how you know whether it's n or n minus 1 or n plus 1 or whatever. Okay, so of course, we can prove that these two definitions are equal, okay? So here are some examples of geometric sequences, right? And here, a is equal to 1. Remember, a is always easy. It's just the first element. So let's do the easy stuff first. A is equal to 3. A is equal to 1. A is equal to 2, okay? And then what's r? Well, 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is, yeah, r is equal to 2, okay? 3. 9 divided by 3, that's 3. 27 divided by 3, looks like r is actually equal to 3 as well, right? 27 times 3 is 81. Yes, we're good. Okay, shoot, 1/2 divided by 1, that's a half. 1/4 divided by 1/2, yep, that is a half. Okay, 1/8 divided by 1/4, yep, that's a half. So actually r is equal to a half in this case, okay? So, so yeah, this is a geometric sequence that's going down, okay? And then this one, what's r? Well, minus 2 divided by 2 is minus 1. 2 divided by minus 2 is minus 1, and so on. R is minus 1. When r is negative, then they're going to flip it and sign, right? That'll happen every time. Okay, so that's those are just some examples how I can recognize geometric sequences.